So there was a bit of an interruption, but the Sx just means the standard deviation of the x variables. So if you completely forgot about the y variables and you thought only about the x variables, then you would find that would be called the S subscript x. So that would be 12.675. And then next, the rentals is the y variable, and you would calculate the sample size. It doesn't really show the sample size directly, but we know the degrees of freedom for regression is n minus 2. So since 6 minus 2 is 4, we know that n is 6. And then the formula that's for this is the standard error of the residuals with n minus 2 degrees of freedom, which would be 0.974, divided by the standard deviation of the x variable, which would be 12.675, times the square root of n minus 1. So n is 6, so 6 minus 1 equals 5, and then I'll go ahead and calculate that. So 0.974 Okay, so 0.974 divided by 12.675 times the square root of 5. And then I get this. Round this off to 3 decimal places. So 0.034. Like that. Okay, excellent. Now we're on to the third problem. So a data set of 5 observations concession cells, so that means n equals 5, and it has this regression slope, and the standard error is 0.0455. So compute the value of the t-statistic. Okay, the hypotheses are the slope, which is called beta 1, equals 0. The alternative is beta 1 if they're talking about a relationship, it doesn't say a positive relationship or a negative relationship. It just says a significant relationship. So it could be either way. So no relationship means 0. Positive or negative means not equal to 0. The value of the t-statistic, just like almost any statistic, it's the value you have minus the theoretical value divided by the standard error or the standard deviation. So the value that we actually got for the slope was this number right here, the coefficient of the variable, the independent variables, which that coefficient is 0.267, and that's called B1. 0.267 minus the hypothesis variable, which is 0, and then divided by the standard deviation of B1, which is right there, 0.0455. And of course 0.267 minus 0 is just 0.267. So then we'll get 0.267 divided by 0.0455, and we'll get 5.868. The degrees of freedom is n minus 2 for the regression, so it would be 5 observations. 5 minus 3 equals, 5 minus 2, it's n minus 2. 5 minus 2 equals 3. And what's the p-value? So to calculate the p-value, we'll need to find the p-value of a t-value, you have to use the t probability calculator. So the t distribution, it's going to be between, so it's 3 degrees of freedom, and we got a t-value of 5.868, and it's two-sided, so let's do negative and positive 5.868, and then compute. Then we'll do 1 minus that answer. So 1 minus that answer is going to equal 0.009, it looks like. 0.0098 rounded up would be 0.010. Excellent. And that p-value is less than 0.05, so we can reject the null hypothesis. Can we reject it? Yes, because the p-value is less than the alpha value. Check answer. Good. Okay, so now a website that rents movies has this scatter plot. That plot looks fairly straight. So, can linearity be checked with a scatter plot? And I would say yes. And it looks straight, so it can be checked, and it's satisfied because it looks straight. Can independence be checked? Well, there's no way to know. You can't look at points and tell if they're independent or not. So equal spread means as you go along this line, do the points start to become farther apart vertically. So these points are spread about maybe 2 or 3 units apart, and maybe a similar distance along the way down. So to me, it looks like the variability in the rentals doesn't seem to be changing very much with age. The variability in the y variable is rentals. Variability in rentals, the y value doesn't seem to change its variation along the x-axis, which is age. Okay. Can normality be checked with it? It can be checked with a normal probability plot, but you can't really check it with a scatter plot. So we want to, the easiest way to do a prediction is just to open the data up in StatCrunch. So I'll do that. And I'll go to stats, regression, simple linear, x variable, number of salespeople working, y variable, sales, and I'll just do compute. So now I'm going to do a predicted value. So predicted value is just plugging it into the equation. beta naught plus beta 1 times x. And x is the number of salespeople. So 12 employees is x. Beta 1 is equal to 0.887. Beta naught is equal to 9.13. So statistics generally at this point, this is simple. So when I'm going to use StatCrunch to calculate that, it's not because it's so complicated. Always understand what you're doing is actually super simple. I'm just using StatCrunch since my calculator, I don't even have a calculator with me right now. So here's stats, calculators, just go to the options, do edit, and click on prediction, and tap in 12. And then it'll calculate that exact same equation for you. StatCrunch is never doing anything mysterious. It's just doing the same simple equations that it shows in the problem. Okay, so the prediction turns out to be 19.77. Now we can make a confidence interval for the mean sales on that day. So edit this again. Okay. Very good. So what is the average sale value? So these two confidence intervals that it shows us, they have different meanings. So what is the predicted confidence interval for the average age? It's 19.01 through 20.53. That's a fairly narrow range. But what about if it was just one day? Instead of the average sales, the mean sales for the days, what's the confidence interval for the sales on just one day? Well, sales change based on what day it is. So it's going to have a lot bigger of a range. So 17 through 22. So for the average sales on any days or all days that have 12 employees working, it's estimated to be anywhere from 19.01 through 20.54. But if you just randomly pick one day, and you don't take the average of all the days, you just pick one day, but you don't know if it's Monday or Sunday or anything, then the prediction for a day is going to have a lot bigger fluctuation than the prediction for the average of all the days. So it'll be 17.37 and 22.17. Okay, so here's a regression equation. The predicted, remember that hat means predicted. The predicted amount of that people will eat out per week is $23 plus 0.274 times the household income. So, wow, that's a rich household. Let's see. So what does that interval mean? It predicts that a customer would spend between $40 to $50. So it means there's a 95% chance that the mean amount spent by people. It's an annual household income. So first of all, this only applies to households with an income of $80,000. So it can't be B. It can't be about the surveyed households because your conclusion is never about the sample. that you surveyed. It's about the population. And it doesn't involve the mean. So we're 95% confident. I'm still not happy with the phrasing of that, but that's the best I can find. Because rather than saying 95% of households, you should say that you're 95% confident that a randomly selected household would fall between that range. Okay, so now for the mean amount spent weekly by people. Okay, so it can be stated with 95% confidence that the mean amount spent weekly by individuals whose household incomes are $80,000 is between that and that. Okay, I like that one. And it's not about the sample mean, it's about the population mean. Continue. The intervals are different because when you're doing an interval for the average of everybody, it's always a lot narrower. So $43 to $47. That's only a variation of less than $4. But if you're talking about one household, it's a range of between $40 to $50, which is a variation of almost $10. So individual households can be very different from each other, but if you average them out, the range will become a lot narrower. So means can be estimated more accurately than the values for individuals. So that range predicted for the average of all the households is narrower. So let's make a scatter plot for the data. Best way to do that is to open it in StatCrunch and do graph scatter plot. So age would be the X variable, browsing time would be the Y variable. Looks like that. So let's pick the graph that looks like that. It would be, looks like that one. I would say yes, I think a linear model is appropriate. But notice that there's a flattening off at the beginning, like that. Then it goes straight down, and then it comes down straight down, and then it flattens off over here at the end. So there's a little bit of a curve at the beginning. So might not be completely appropriate, but it looks mostly straight. So let's find the equation of it. So to find the equation of it, we'll just do, we'll just do stat, regression, simple linear, X variable, age, Y variable, browsing time, and click compute. So the intercept is called B0, that's right there. And then the slope is called B1, it's right there. And then I'll round those off to 1 decimal place. So 0.7 rounds up to 0.8. Negative 10.78 rounds down to negative 10.8. Oh, sorry, the age coefficient to 3 decimal places. My fault. Constant to 1 decimal place, age to 3 decimal places. I almost missed this one. You always have to make sure you read what it says in the parentheses before you check your answer. Negative 10.780. Okay, then Let's change some of the options right here. Graphs. Let's just do all the graphs. Select them all. Compute. So when you do linear regression and you do the options and you make the graphs, it shows all kinds of cool stuff. So interesting. So I would say this is a plot of the predicted values versus the residuals. And I don't really see any pattern. So I would say that seems satisfied. Then let's look at the normal probability plot. That's also called the QQ plot. So this plot looks a little bit somewhat curved a little bit, especially at this point right there. It's not really on that line. So I would say it's not real. If it has to be really straight on the QQ plot or the normal probability plot in order to work. So I'd say the normal condition is not satisfied because the normal probability plot does not show an approximately straight line. Another way of seeing that is the histogram of residuals. This is skewed to the left, so it's not symmetric. In other words, it is unimodal, but it's not symmetric. But the histogram of residuals is not unimodal and symmetric. And then let's see. Let's look back at the normal probability plot. I don't really see any extreme outliers on there. So I'd say the outlier condition is fine. You could also look at the scatter plot. I don't remember seeing any outliers on the scatter plot either. So does not show any extreme outliers. Okay. Actually, let's see. No pattern. Actually, I'll say the normal condition is satisfied because the normal probability plot does look fairly straight. Let's try that. But if that's the case, then this one, it's obviously skewed left, but if you look at the little line they drew through it, it actually looks fairly symmetric. If you change the categories, for example, if you change this from -20 to negative maybe 18, then some of these data points in this box might fall over into that box, and then it might look a lot more symmetric. So let's try saying the histogram is unimodal and symmetric. Okay, try that. Excellent. Okay, now plots. Runtime predicted n-scores. Okay. So the formula would be the intercept negative 27.55 predicted budget equals the intercept plus the runtime coefficient, which is B1, times the x variable, which is runtime. Then explain it in words. It suggests that millions, that's in millions of dollars. So it takes $0.68 more million approximately for every unit of runtime, and what is, I'm assuming it's probably a minute of runtime. Probably a minute, it doesn't really say. Yeah, minutes. Okay. So that costs about 0.68 million, which is 680,000 per minute. That's right. And then the intercept is negative. No. Yeah, the intercept is negative. So if you had a video that didn't even have anything in it, it was 0 minutes long, then it would cost a negative amount of money. So that would be negative $27.55 million. That'd be awesome. Doesn't make any sense. It doesn't make any sense, but let's look at the output again. So the p-value of the intercept is more than 0.05, so this is not, that intercept is not really as significant, and it also doesn't make any sense. So it's meaningless, and because the p-value is large, it's not necessarily significantly different from 0. So it might actually cost $0 to have a video that was 0 minutes long. The output reports that this S equals 16.68. So this is talking about the standard error of the residuals. So the discrepancies between the actual budget of movies versus the predicted budget is about $16 million. So some movies cost $16 million more than average, more than would be predicted, and some movies are the opposite. They cost less than predicted. So the amount by which film costs differ from the predictions. That's exactly right. The actual film costs, the difference between the actuals and the predicted values, have a variation of $16 million. And then, what's the value of the standard error of the slope of the regression line? That would be 0.18. It's nice, it actually tells it to us. 0.18. Explain what this means. That means. Well, ouch. Explain what that means. So first of all, think about what the slope means. The slope mean is 0.68. That means that it costs about $0.68 million per minute of runtime. But that could vary, though. And 0.18 of $1 million is $180,000. So the slopes of regression lines based on other samples could vary by about 0.18 million, which is $180,000 per minute. And there we go.